We're going to skip ahead in the chapter anyways, to section 7 of chapter 7 on linear inequalities. We'll go through the middle later, but this seems to work well with the beginning of the chapter. So at the beginning of the chapter in section 7.1, we looked at linear equations and how to solve systems of linear equations. In this section, we're going to be looking at solving linear inequalities and linear systems of linear inequalities. So very similar, just with an inequality instead of an equal sign. Our first example, we've got y is less than 2x minus 3. One thing about an inequality, kind of like we've done in the past, where you had something like x is greater than 5. There's an infinite number of solutions to that. X is greater than 5 could be 6, 7, 8, 5.2. We have the same issue here, where we can't list all the solutions to this linear inequality. There's an infinite number of ordered pairs, x, y, where this will work. 2 times 5 is 10. 10 minus 3 is going to give me 7. So y could be 6, and x could be 5. Y could be 4, and x could be 5. There's an infinite number of pairs that would work. So we're going to graph it. We can't list all the solutions to this. We're going to graph it. We're going to graph this line here, 2x minus 3, just like we would if it was a linear equation. We have y is isolated, y is by itself, which makes it easier to graph, where we have the y-intercept at -3. We've got the slope of 2, excuse me, and that would work. And so the y-intercept, -3, there it is. And the slope of 2, so we go a rise of 2, a run of 1. There's my second point. One thing you have to be careful of before I make this line, though, connecting those points, is that since it's an inequality, this says y is less than the line, but not equal to. And so no matter what ordered pair we have here, like the ordered pair 1, -1 would not work, because 2 times 1 is 2, minus 3 is -1, but it equals -1. It's not greater than -1. And so because this point and every point on this line won't quite equal that line, it's just a little bit too big, we use a dashed line. When we were doing inequalities before, if it didn't quite equal that number, we used an open circle. We used a closed circle to represent that it did equal, less than or equal to. Or greater than or equal to is a closed circle. Less than or greater than was an open circle. Same idea here, except our open circle is a series of open circles. It's a dashed line. So dashed line is just less than or greater than. Less than or equal to, greater than or equal to would be a solid line. Now we need to shade in all of the results. So this says y is less than the line, which means all the y values below that line, all the y values that are less than that line, would be considered appropriate y values to use. So we're going to shade below the line. So my way of thinking about which way do I shade, above or below, is that this says y is less than the line, y is less than that line. So I shade below the line. And that's how you graph linear inequalities. Let's look at a situation. So Sarah can spend at most $7.50 on vegetables. Let's talk about that word or that term at most. Typically, when we say at most, we mean that less would be okay, and equal to is acceptable. So if you could have at most 5 people in your apartment, 2 people would be fine. 2 people would fit, but 5 would just barely fit. 5 would be okay. 6 would be too much. And so if you have at most of something, it means less than or equal to. The other side of it that we use when we're talking in English is at least. So at least usually means like I need to make at least $100 this weekend or something in tips. So at least means more would be great. If I made 200, that'd be awesome. But I can't make less. I need to make at least $100. So at least means greater than or equal to when we use those terms in English. So Sarah can spend at most $7.50 on vegetables. She can spend $6, but she can't spend more than $7.50. Broccoli is $1.25 a bunch, and carrots are $75 per package. I'm going to use B for broccoli and C for carrots. You can use X and Y if you want, but I'm going to use B for broccoli and C for carrots. So $1.25 times every bushel of broccoli or bunch of broccoli, and 75 cents for every package of carrots. So I'm going to have this inequality here. $1.25 times each bunch of broccoli, 75 cents times each package of carrots is less than or equal to $7.50. Because again, you can't add these together and spend $8 if you only have $7.50. For graphing, you have some options. C and B aren't designated to be which one has to be the y-axis, which one has to be the x-axis. So if you're going to graph this, you could get either C or B by itself. You could isolate either of those variables. It doesn't really matter. There's no set way to do this. I'm going to choose C. I'm going to isolate the carrots. So if I subtract $1.25B and divide by 75 cents on both sides, I get this. Now, I left my decimal divided by a decimal as a fraction because I need a rise and a run to graph. That makes it a lot easier if I have a fraction. Fractions are better. Some of you maybe disagree with me, but fractions are better, especially for graphing. Now, I chose to get C by itself. I chose to isolate C, which means that C, the carrots, has to be my y-axis on my graph. And broccoli has to be my x-axis on my graph. And that is important that you label your graph. If you use carrots and broccoli, if you're talking about adults and children or whatever the two things we're comparing, you need to label it because you could have just as easily got broccoli by itself, subtracted $1.75, divided by $1.25, and you got a different inequality to graph. So make sure you label your axes when you're dealing with a situation problem like this. Now, it says that it could be at most 750, so it's less than or equal to. So I have a solid line here for my graph line. 10 was my y-intercept. There's my y-intercept of 10. My slope was negative 5/3. So I went down 5 over 3, down 5 over 3. There was my slope. And I shaded below the line because it's C is less than the line. So I shaded below, which also makes sense. If you have $7.50, you can't spend anything up here. You can't spend an infinite number or buy an infinite number of carrots or an infinite number of broccoli. It wouldn't make sense to shade above the line because you'd be going to infinity, and that'd be a lot of carrots. And so we want to have below the line. One thing, I think this is going to come up in the assignments too, that we have to ignore a little bit just because it's a computer, is this less than 0 bit down here, down here. The shading should technically stop at 0 because you can't buy negative broccoli and you can't buy negative carrots. And so it technically should stop here at 0. My graph goes beyond that simply because I wanted to show the numbers. 2, 4, 6, 8, 10, 2, 4, 6. And so it should stop here at 0. All right, let's look at another problem here. We've got two different inequalities that we can solve. We can try and solve this system and figure out what x and y values would work for both of those inequalities at the same time. One way to do this would be to isolate the variables, to get y by itself for both of these and graph it, and that's probably what I'm going to do. But another way you could do it is find the x and y intercepts. You could set y to be 0 and say x would have to be 4, pretend it's an equal sign, say x would have to be 4. That means when y is 0, x is 4. There should be an x-intercept right here. When x is 0, y is 4, so the x-intercept would be right here. So if you find the x and the y-intercepts and graph it that way, pretend this is an equal sign and set it up in the same way. You can do the same thing for this one. I isolated the variables just because that's my natural inclination to do. So I subtracted x from both sides and got my y's by itself. So the y-intercept, sure enough, is 4 for the first one. I think I did the first one first. Yep, there it is. And the slope is negative 1, so down 1 over 1. Now, because we're going to have lots of lines, and they're going to intersect at certain points, and we need to figure out where it's shaded and all that, I would recommend going and doing more dots. So I would add some more dots to this if I were doing it on paper. So I'm sure to get the right line. It's going to be a dashed line because it's less than and not equal to. So there's my red line. I'll shade in a little bit. So here's the next inequality here. Y-intercept at 3. Boop. slope of 1, rise of 1, run of 1. There we go. This is less than or equal to, so I'm going to have a solid line. I'd also recommend doing this in pencil, because if you draw the line and go, oh, shoot, it should have been dashed, it's a lot easier to erase and make it a dashed line with a pencil than with a pen. Okay, shading. For the second one here, I think I did the second one first. Well, for either one, really, y is less than the line for either one. So I should be shading below the line for the blue and below the line for the red. There's the blue. So again, y is less than or equal to x plus 3. So I shade it below the line. Y is less than the red line. So I shade below. Now, this area over here on the left is shaded red. And so all these ordered pairs over here are solutions to this inequality, this first inequality here. However, they're not solutions for the second equation. Same thing on the far right. All these solutions shaded in blue are solutions for the second inequality. We want where they overlap. Now, if you don't have two colors, that's okay. What I typically do when I'm doing this on paper and I don't have two colors is I make diagonal lines going in one direction, maybe going down to the left, and then after the other one, I go diagonal lines down to the right. What ends up happening is the two diagonal lines will cross at some point, and those crossings, that almost hashtag pattern that you're going to get with diagonal lines, is my overlap. So that's what I tend to do, is I do diagonal lines one way, diagonal lines the other way, and where they crisscross is my overlapping shading. All right, so what I'm going to ask you to do is I'm going to ask you to write an inequality for these two graphs. So two graphs are shown. Both of them have two inequalities. So there's a red line here and a blue line here, and they intersect down there. There's a red line here, there's a blue line here. They intersect right up here. Write a system of linear inequalities to represent these graphs. I'm assuming you paused it. I'm assuming you tried it on your own. One thing to be careful of before I put the answers up, that on the left side here, both of these lines are dashed. I don't know if you can see that very well. And on the right, one of these lines is a solid line and one of them is dashed. So if you want to pause it and make any fixes for that, go ahead and do that. Here are the solutions. And I will talk more about where those solutions came from in a follow-up video. All right, special systems. I think I've got two more slides here. Special systems. We talked about parallel lines in the other video on linear equations. And so if two linear lines are parallel, they will never intersect. There's no solution. It's an inconsistent system. And that's what we have here. So y equals 2x plus 1, y equals 2x minus 4. They have the same slope. They're parallel, different y-intercepts. It's an inconsistent system. With inequalities, that's not necessarily the case. They can still be parallel lines, and we can still get solutions, or not. And I'm going to show you what I mean, because there's 1, 2, 3, there's 4 ways that this could happen. Here's one way. If they were both shaded below the line, both the blue and the yellow are shaded below the line, all the solutions for that system are going to be down here below blue. So it's kind of like a redundant system. It's basically just this second equation. All the solutions to this second equation, or inequality here, excuse me, are the solutions for both systems that work for both of them at the same time, because anything below the blue line is also below the yellow line. So that's one way that this could turn out, where, yeah, we've got solutions, they're all down here. Another way is if the first equation, the yellow line, is below the line, is shaded below, and for the second equation, the blue line, it's shaded above the blue line. In this case, the solution set is in between the two parallel lines. So it's not below, it's not above, it's in between the two parallel lines, and all the possible solutions are in here. Another way it could happen is that there are no solutions. If one's shaded above and one's shaded below, now there are no solutions. So it is possible to have parallel lines that do not have solutions. It's also possible to have two parallel lines that do have solutions. So really that shading is important. You can't just assume that the special situation, the special system will not have a solution. It might not. So be careful with with parallel lines that are inequalities. Don't assume that there's no solution. Last thing, systems with 3 inequalities, or 4 or 5 or more than 2. Nothing changes, we still do the same thing. This is where colors definitely come in handy, but you could certainly do other patterns with your shading. So y is greater than or equal to x minus 3. The y-intercept is -3. So right down there. And the slope is 1, rise of 1, run of 1, rise of 1, run of 1, and so on up the pattern. It's a solid line because y is greater than or equal to the line, and I shaded above the line. So there's that first inequality. Y is less than or equal to 3. You'll notice there's no x value here, so there's 0 slope, 0x, because this would be like y is less than or equal to 0x plus 3. So the y-intercept is 3, but since it has a 0 slope, it's going to be a straight across horizontal line. Y is always 3, solid line, and its y is less than that line, so y is going to be, and really that makes sense. Y is less than 3. Well, 2, 1, 0, -1, -2, all these y's are less than 3. Similarly, x is greater than or equal to -4 means that all the x values, 2, 3, 4, 5, 6, -1, -2, are all greater than -4. So I'm going to shade to the right of -4 with that straight up and down line. Remember, I had an undefined slope if it was an x equals or an x is greater than or equal to. We're going to have an undefined slope. The solution set then is this triangle in the middle here. It's where those 3 intersect. So all the solutions, all those shadings intersect right here. So a system of 3 inequalities could look something like this. I'm going to stop there and let you do some practice.